kind of go over some of the things I hope to cover today, because we have today and next week. That's going to be our last meeting. And, I want to cover as much as possible, especially in the more difficult topics. And you have the manual, you have access to the book. You can continue to ask me questions. I can run small sessions here and there if you want, specific topics. And can share it with the students as well. So hopefully we will cover everything, as much as possible. We knew that we couldn't squeeze everything within 6 sessions of 2 hours, but the plan was to cover as much as possible. I felt that the modeling topic is important, and I didn't want to skip some of the other surface creation commands like Loft, which I think is very important. And I'll run it with history, and that will give you an idea about the limitations and the possibilities with history. So this is one area I hope to cover today, or I will start with. The other thing is blocks, and how to create those, and to help with the more detailed modeling, and to keep the model more lightweight. We can continue to do more detailed modeling with the floor plans and the details and the figures, but I thought perhaps this is more of a repetition of the same set of commands, and probably our time will be better served if I give you a quick introduction to Grasshopper as a parametric modeling tool. So this is how we can, we'll hopefully end today with some Grasshopper. For next week, I'll need your input. I'm thinking we might be able to kind of have an overview of visualization and 2D modeling. So we'll split the 2 hours into in these 2 topics, which I think is important for the architectural modeling workflow. So that's probably as much as we can squeeze. And if you have other topics or areas that you would like to be covered and it's important to what you do, let me know ahead of time before the class next week, and we can change the topics to what you need me to do. So does that sound like a good plan? Yeah.
Yep. Yeah. Also, I think, yeah, we have everyone, almost everyone here now.
Okay, perfect.
Yeah.
So we can get started. Let me just minimize that thing. Okay, so last week we ended up with creating this patch that is a patch surface that has parameterization. You see these red ISO curves, which is the U direction, and the green ones is the V direction. And you can see that this is a trimmed surface. And the way to check that is to turn on the control points. P on is the shortcut for points on, for control points. And as you can see that all these, the control points are outside the actual patch. So if you untrim and pick on any of the edges of the patch, you'll see this is the untrimmed surface. And this is the outline of the portion of the surface that is active. So I'll undo. And it's okay to work with trimmed surfaces, but sometimes you'll find some limitations there. So if you are, you want to generate a certain kind of like panels and that's going in certain direction, it's hard with this kind of surface, with the trimmed surface, to kind of deal with that kind of situation. So many times, if you can get away with it, try to create untrimmed surface. You'll have better control overall. The other thing is that when you turn the control points on, you can see that if you select some of those points and say, I'll just move them up. Those have no effect on the active region, but let's say we select a few points here as well. And you can see that sometimes it's not as predictable to see what change is going to happen when you have untrimmed surface. So I'll demonstrate on the side a little bit to show you how this can be problematic. So I'll create a plane here. And I'll trim that plane with this circle. I think I have some guides here that I want to remove those guides. I don't think I need them. Anytime I create anything, my guides highlight, and in that model, I have created some guides to help me model. So I'm just gonna remove all of them. So if that's my curve, let me kind of scale it a little bit, trim. And this one. So I trimmed this plane with this circle. Now, if I turn the control points of the plane and move it to the side, as you can see, the hole in the middle, which was circular, now it's kind of distorted a little bit, and it's just following the surface itself. So there is an implication when you trim a surface and try to modify it afterwards. Just keep an eye on that thing, because if this is not a desirable thing to do, then you kind of need to pay attention to that kind of behavior. So what we will do is we will try to recreate that patch surface using Loft. And Lofting give you a lot more control, as I mentioned. Remember when we created the patch to start with, it was not symmetrical, and there is a chance even the one that used the base plane is not completely symmetrical. And we will use a different method to generate the surface. I'll just drag it to the side just so that we're not distracted by the building, and we'll just focus on the surface itself here. So there are some very important curves here that we use. Before I do that, let me just pick the curves as well. Curve. 1, 2. Is there any side curve? Yes. So I'll just copy all those to the side. So now I have my surface. I have that curve, and I have also another curve to the side. All right. So how can I create the loft curves? Loft command in general takes multiple curves, so I'll just create lines. And just to show you how this works. So I'll create a bunch of lines. And Loft command basically ask for a number of curves as input, and you can dictate the order of selection. And then it generates a surface that goes in between these curves. So they don't have to be lines, obviously. And there are some options to help you simplify the output, or you know, what is the amount of fitting you want within the curves and what have you. So this is basically how Loft Command works. So what we need is a number of curves that go across here, like cross sections, and be able to loft between them. Let me hide the ISO curves here. It's a bit of a distraction. If you are given a surface, one of the things you could think of is to extract ISO curves to be able to get to some of these curves. But as you can see that, and this is useless in this case because the direction of the curves is like that. And that's not what I'm looking for. What I'm looking for is something that go in between those two extreme curves, this one and that one, right? So before I do that, I'll simplify these two curves so that when I create a tween curves between them, they will have a simpler kind of structure. I can do it before or after, but let's go ahead and rebuild these two curves to have a degree 3 is fine. Degree 5 is what we used initially to make a smooth curves, but we can go with degree 3. And point count 8 sounds good. Okay. So as you can see now, the two curves are a little simpler. We didn't lose much really in terms of their location. And since this is a conceptual model and we have some room to make it, you know, slightly different than the sketch we had, that shouldn't be a problem. So I have my two curves here. The other thing is, if you see that those two curves kind of meet in one point, and this is going to be difficult to eventually be able to cut through or make the panels in between. So perhaps it's better if I move this a little bit, and this will give me some space to be able to generate the curves in between. So maybe I'll have it a little closer though. That's just enough. And I'll use a Tween Curves command. Tween Curves, it creates curves in between the two curves, two extreme curves that you select. So this is my starting curve, and this is my ending curve. And it's saying, what are the number of curves that you'd like to go in between? You know, 5 sounds reasonable. And it's asking me what kind of, you know, this is the output layer, which is the start curve. Okay, let me exit the command here. I want to create a new layer under the roof, under the loft. No, actually under the roof. Let's create a new sublayer and call it reference curves, loft curves. Okay. So these are the two extreme curves. I will change their layer to be the reference loft curves. And let me change the color of it to be red so I can see it more clearly. And I'll make this to be the current layer. So Tween Curves. And this is the start, and this is the end curve. And as you can see that the start and the end, they have two different directions. You already can see that the directions are different. But now if you click on the end, you know, you get a proper preview. Another thing you can do is to check the direction of the curve before you start. So dir, direction command, you select the two curves that you have, this curve, and this other curve. And you can see, well, actually they sort of go into the same direction. So I don't have a direction problem. Maybe I flipped in the middle of the tween curves. So anyways, if you have two different directions, you can flip one of the curves so you have consistent direction between the start and the end curves. Tween curves, this is the start, this is the end. And it's actually, flipped in my case. So I'll just click on one of the ends so that I get all the curves going into the same kind of direction. If you zoom in, as you can see, those are trying to kind of fit these curves in between these, equal distances in between the start and the end of the curves. Press enter. And let me just use ghosted so I can see through a little bit. Yep, let's ghost it. So now what I have is a rough or an estimate curves in between. They are not on the surface, which, I kind of like these curves to be on the surface and following these this contour, the edge, the other edge. So one of the things we can do is to project these curves into the surface itself. I'll just use project command. And I'm using my patch surface as a reference to help me generate these curves that I can use for Loft. So I'll select those curves that I want to project to the surface and delete the input, yes, and output to the current layer, and direction is C-plane Z. All the details are correct. Press enter and select my surface to project to, which is the patch surface. Press enter, and as you can see, it was projected and trimmed. The only thing is that towards the other end, as you can see, those curves ended up going to to the surface itself. Well, I really wanted them to be along that line, so I'll just draw a line here, and there are probably other ways to do it. So if I divide that curve into perhaps 6 segments, I think. And what I'll do is I just want to drag the end control point of each one of those curves to be aligned here. And this will give me a better, here's my control point, and I drag it to the point itself. That will give me a better kind of form that I'm looking for, as opposed to ending in one point the whole surface, which is very hard to build, and it's kind of not very realistic. Those look like good curves to me, and they follow the kind of shape that I'm looking for. And I don't really need more than just half the surface, to cover half the surface, because I can mirror these curves and make them symmetrical. Now I'll introduce an idea or a functionality here in Rhino, which is history. If you look down at the status bar here, there is record history. Right click on it. And it has the option to always record history. You don't want that. You just make sure you check the update children, lock children, and history break warning. I'll explain how history works as we create the lofted surface here. The idea is if you have history enabled, and for example, you created a loft out of curves, if you go back and edit these curves, the surface will update with it. So it gives you some parametric control, but you don't want to overuse it and have multiple layers of control. So maybe two layers is fine. Create a loft out of curves and then offset that surface solid to create the solid of the roof. But if you keep doing or piling other functionality, sometimes it's hard to keep track as to what we started with, and things start to break, and you don't understand what happened. So, but in this particular case, because we want to sculpt our surface, then it might be useful to use history in that particular situation. Use it carefully and pay attention when the history is enabled in some cases. So we know we want to use history, and we're using these reference curves to create the loft. But before we can create the loft, we need to mirror these curves and then create the loft. We can record history with mirror command. Notice not all commands support record history, but most of them are Rhino. So you press record history once, it's going to record for that particular command. So you need to press it before you start the command itself. I'll call mirror command, and I'm selecting my curves that I would like to mirror, and press enter, and I will mirror around the center curve. As you can see now, the curves are all mirrored with history. So for example, if I move this away, the last curve, the mirror curve, moves as well. Now that I have my curves, I'm ready to do the loft. But before I do the loft, let's make sure that we have simple and nice curves. If I select the curves, you can see that the curves, the center and the end curve, because I already rebuilt, they are kind of simple and nice curves, but the interior ones are not. So actually, before mirroring, I'm going to select these curves and rebuild to be matching to 3x8, the other end curves. So this way I have a consistent, and it's easier to do any modification with less control points. If you have too many control points, the NURBS curve is kind of doesn't look as smooth when you try to kind of edit it. Let's make sure also the direction of all curves are going in the same direction. You can see that the two end curves are going one direction, while the interior curves are going another. So I'll just click on the curve end here and here to just make sure all the curves are going in the same direction. That helped me create a more clean kind of loft, and I don't have to do realignments and what have you. Now the curves are ready. I am ready to do the mirror. Remember to click record history down here. It becomes bold, and you go mirror command, select all the end curves and mirror around the center curve. So I'm using the 2 points. As you can see here, this is mirrored. And just to check, I'm just going to move the end, and you can see the end moving there as well. Now I have the bones, if you will, the curves that will help me create a lofted surface. And I know for sure it's going to be symmetrical, and I have a bit of control to change it or edit it after the fact because I'm using history. So again, click record history, call Loft Command, and just select the curves in order to create your loft. Press enter. And you have the loft options. So you can say, I don't want to simplify it. I just want you to follow the control points because I already created them in a certain way that I'm comfortable with. But if you have you know, you want to rebuild them with different kind of resolution. Instead of 8, I want to 12, for example. You know, you change the complexity, then you can do that as well. So that's one of the things that you can also do. I'll just select the original patch surface that I had, and I'll just hide it here so that we only look at our loft surface. Actually, I'll show it and I'll just move it because then we can compare when we do when we analyze the two surfaces. Let me move it in the green direction, just to the back a little bit. And now we have our two surfaces. This one is created out of a loft, the red one, and this one out of a patch. Let me turn off the ISO curves. Oh, actually, as you can see, the ISO curves now are going in more, you know, controlled direction that we are interested in. I can turn off the ISO curves. And if I do surface analysis, analyze surface curvature analysis, and select my two surfaces, let me adjust the mesh to be maybe 5,000, just so that I have a bit of a smooth mesh. You can see that the two surfaces are, you know, generally similar, but you know, definitely, you know, the loft surface is more symmetrical, but you can see the green parts are more developable parts of the roof. But as you adjust your curves, for example, if I move that up a little, you can see that your surface also updated here, because you built it with, we built it with the history enabled. If we don't like that pointy end, you know, we can change that a little bit. And you can see it is updating in both directions. So we are keeping the symmetry here and the control based on, you know, the NURB surface that we have just created using history. And this is how you can create, you know, the loft surface for the roof using the loft command. Okay. So these are the main ways to generate NURB surfaces, you know, using the patch, using the loft. There are other ways depending on the situation, but these are the more common ways. Of course, we have the revolved surface, we have the planar surface, but for a freeform surface, this is probably the two most used surface creation methods, right? So that basically covers that section, which how to create a loft surface and how to use it with record history as well. And that becomes your final roof surface. Obviously, you can just take it back. I can just move my surface back, and I'll use that. Well, the top point I actually changed. So let me just, that original one, I'll move it back, and I have a reference here at the top here to go back to the top curves there. So that would be the location of my surface. Did I move it? Move from the center here to there. Unable to transform because, okay, that's great. Because we selected in record history to lock the children, if I only move the surface, it doesn't let me because it is built based on my my curves, my underlying curves. So I should select all the curves because these are the building blocks of my surface along with the surface. And actually, you don't even have to select the surface, just the curves, and perhaps even just the end curves here, these curves, because all the other curves are locked because we use mirror command. So if I select only these central curves and move them using the end here and this, it didn't quite work. Why? If I move this here, that will be, oh, because I mirrored along that plane and that plane was remembered. So unless I break history at this point, I cannot move my surface. So what we can do is with the record history, you don't lock the children. You can see no locking the children. And now I can break history. So I can move my surface. And this is an example how sometimes it's a bit complicated and you get that warning that the move command broke the history of one object. I'm okay at that point because I actually, reached my final surface. So I just don't need the history. But I moved it away. You should like create it in place and you will not encounter this problem. But at any rate, I just wanted to just move it in to show you how the surface is going through the platform, which is great, so that when you create a thickness, you can trim out any additional. So don't really make it align directly with the flooring. Allow some allow it to go through. So when we do offset, offset surface with the solid option, and you can delete the input or you can keep it, the surface, and you can make it loose, if you want. You don't want it too rigid, and you can just specify the distance of it and press enter. This will generate the thickness. I'll just go shaded. And as you can see, you have the thickness now, but because you allowed a little bit to go through, I don't know if we allowed enough. Let's just select that part, which I have locked. If I select that part and move a little bit nearer. You can see the intersection, and let me use ghosted here. You can see that intersection. So it's much easier now because we have that going through a little bit to Boolean split. So Boolean split. And this is the poly surface we will split. And this is our cutting one. And this way we can get rid of that part. And we have a clean intersection between the roof and the platform here, as you can see. Let's see if rendered view is going to give us a little bit better. So as you can see, that intersection is very clean for the surface with the flooring. So sometimes you just need to kind of leave a little bit of an extension so that it's easier to cut. This one also need to be cut, but you get the idea here. Is there any question related to surface modeling or surface creation, Rhino, before we move on to the blocks? I guess I can expand that a little bit to see if anybody is moving their head. Was that clear? How to generate the loft with history and how to modify that surface and how to create calculate the thickness of the surface? Yeah. Yeah. Okay, great. So we are ready to move to the creation of the staircase here. So I sent you a file, which is the stairs blocks that shows, you know, stairs that's created using the blocks. We will recreate everything, so I'll just hide the steps and turn on only the scaffolding part. And you should do that as well if you want to follow the modeling. This initially we had just that outer circle, and the distance was, let's remind ourselves, from the center to the end here, it's exactly 1 meter. And what we did here is created for the scaffolding 2 other circles, which is one with a radius of 15 centimeters and the other one with a radius of 95 centimeters. So that leaves a step width of 80 centimeters, 0.8 meters. And, you know, it depends on your design. Obviously, you can make it bigger or based on the requirement, but that's just an example to show how to generate a spiral staircase. And, you know, you have that base curves or you know, scaffolding to help you build that staircase. So in the guide, if we go down to detailed modeling, that would be the page 71 is where you have the steps to generate the staircase. You can use the top or the bottom based on, you know, as your first step, but it doesn't matter in both cases, you know, it's up to you. And once we have the scaffolding, which is the first step, now you need to create the curves for the first step. And we use the scaffolding for our calculation. So we need to draw some arcs, and we can calculate if we want 1 full rotation for our steps, then that's 360 degrees, and divided by the number of steps per full rotation. And let's say if we have 12 steps, for example, then this is the angle will be 30 degrees. That's just a kind of simple calculation just to give us an idea of what kind of you know, angle are we going to use for our arc. Call arc command. And obviously before you do, I'll create a layer here under it to have step curves, for example, I'll call it. And we're doing on top of those because they are hidden, but we're basically recreating the geometry that we need to generate the steps here. So I'll make this step curves as my current, and the color of it, I'll just make it maybe red, so I can differentiate real quickly. I'll create arc. And the center is the center of the staircase. And what I need is to generate an arc with 30 degrees. Remember, we set up our ortho to be angle 30 degrees. So that is very helpful because this way we can just snap to the 30 degrees as we creating the angle for our arc. So the ortho angle is 30. Now I can snap to that angle, and I know it's a 30 degrees. Or I can type 30 And actually it goes into the positive direction. So if I wanted to go in the other direction, I need to type -30. And that will give me a bit of a reference to the angle of my arc. So I can press enter, and that generated my my little arc here. Let me turn on the gumball here. So you can see this is the first arc for my step. I'll draw lines from the ends of the arc to the center of my staircase. Now I have these three. I can join for now, just so that I can move them together. So just to show you, gumball on, this is what we created here at the ground floor, right? Now this is not really my step, because my step need to have that little arc here down the bottom, but as a matter of fact, just because of the shape of my step, I'll need to create you know, two arcs, and you know, the circle in the middle will be the hole, so that we can create that surface of the step, and you know, we extrude it. So it's not very you know, the simple one, because it's going around the middle pole that we have. So what we need here is to create other arcs. So arc, again, from the center, from here all the way around here. That's one. And the other one is perhaps I can create a circle, and it probably is easier to use the center, and maybe 0.2, depending on, you know, the thickness that of your or maybe even smaller. I'll do the 0.1. I'll do more an inner circle here, and assume my pole to have 10 centimeter radius. Press enter. And these all are assumptions I'm making. When you have your proper, when you're doing detailed modeling, you have your dimensions and the material you are using, and you can follow that. Now, I'll need to trim those curves so that I can work with them. I'll turn off the scaffolding so it's easier for me to see my curves. So I'll use trim. And what I want to do is to be able to trim, that's my cutting object. And I want to be able to trim those two parts of my step, press enter, and then I can join those together. And if I select them along with the middle circle and call planar surface, that will create the surface for my step. And once we have that surface, which is in this step here, we can extrude it. So extrude surface, and I can extrude it upward by 0.08 or any thickness of my step. So that's, you know, how you decide the extrusion. So I'm deciding it's going to be 8 centimeters. So press enter. And that basically created the solid for your step. I'm just turning off the ISO curve so I can see it more clearly. And that's the first step that you have. All right. So you will need to calculate the step rise. Remember that we have floor to floor height to be 3 meters, and the number of steps are 12 steps. So the rise is going to be 25 centimeters. So perhaps that's too much, but you know, you get the idea of how you can calculate that. So the first, and if this was the floor plan, let me first move it downwards so I can exactly move it up, because this is going to be my first step. And let's say the C plane is aligned with the step. I can move it vertical from any point by 0.25. So that my first step will be basically elevated by 0.25 meters. Okay. If I turn on the scaffolding, as you can see, that's kind of the first step that I have. And maybe you want to kind of rotate it by 30 degrees if you want the step to start, you know, in a horizontal. Let's do that. Rotate. It depends on what you want to do, but you can rotate it a little bit so that, you know, the first step will be aligned with the entrance of your house. So you know, it doesn't matter, but it's, you know, that's something you can do as well. So once I have my first step, now how can I create the rest of the steps? And you know, the array polar command is really convenient in this case because it does offer you an option to do a Z offset. And we can just say that we want to create 12 steps, and the step angle, we already have it, and the offset to be 0.25. And this way, the whole stairs is going to be created. So run array polar command and select our step. And the center of the polar array obviously is going to be there, this point, this center point. The number of items are 12. Perhaps we need 11, but let's see. And the angle to fill is 360. And the Z offset, we want to set it to 0.25. And the step angle, we want it to be 30 degrees. Okay. And it does give you a preview of your steps. And that looks right to me. I'll press enter. And this is the steps all created. Right. Well, one of the things I could have done before generating all that is to also have the poles of each one of the steps, and I can select that to be created there. But yeah, well, we can do it again now here. For example, if you have a cylinder, let's just undo. And I'll create a line here from this end to there. Oops. Line from here to here. I'll use the center of the line to create you know, another line. And I can use it as a reference for my cylinder. So I'll create a line from the center here, and it's going to be a vertical line from the center. And the height of it could be, I don't know, 1 meter or something, you know, whatever you want it or need it to be according to your standard. And that's the end of the line. So that's my reference line. I can even create a point towards the end to be able to use it as a reference. So this is just part of the scaffolding, and you can keep it in a separate layer if you want to hide it at some point without deleting it. I'll create also a cylinder and use that bottom center, and it's going to be I don't want the center snap. I just want the mid. So, you know, maybe just say 0.05 or 0.25. And the height is to be all the way to that point. So that's going to be you know, my handle. So now that when I do the array polar, I have some more geometry that I want to take with me, and so I'll just do array polar again. And in this case, I'm going to select the step and the cylinder, and also that point, because I can use it as a reference to do the handle, overall handle. Press enter, and that's my center. And as you can see, the number of items 12 from the previous, and the Z offset and the step angle is 30, and that's, you know, exactly what I'm looking for. Press enter, and as you can see, it's all just been created. So you can use Interpolate Curve command to be able to kind of snap to these points, and I'm just gonna right click on point so that I can snap only to points and hide my smart track, and this way I can just snap to these points immediately and create my handle. I'm selecting the points one by one here, and maybe from the top view would have been easier, but I'm snapping to the points, and this is all of them. Press enter, and then I can pipe through this and have a radius to be 0.025, and the end radius, and press enter, and that just created my railing. That's really, you know, you will need the central pole for the I'll create another layer here for the pole, and okay, sorry, that's the pole.
Rajaa, that
Yes.
snaking rail, did you use the curve command? Like, what command did you do to?
Interpolate curve command. So under curve, you can create a curve by interpolating through. So where's the freeform one? Interpolate through points. So interpolate curve. Interp curve is the command that I used, and you can select the points and interpolate. It forces the freeform curve to go through these points. Yeah. So yeah. So well, yeah, we just wanted to create the pole here, and I just want to change that to be pole 1. And I'll just create a cylinder and snap to the middle here. And that's the radius. And I don't know, the height will be maybe 6 meters all the way to the ceiling. So that's basically where it goes, and we can move it to the pole 1. So let's just go render it, and you can see that's basically the staircase that we just created. The one problem with it is that we repeated similar geometry, and that will you know, create all this geometry in the file, and if you have too much of it, it's just going to make the file very heavy. So the other thing is, if I want to change, for example, the thickness of the step, and you know, if you select that you know, step and you move it, and you want to make it thinner, for example, so from here to here, you see that I affected only one step while the rest of them continue to be the same thickness. So this is very limiting, and you see that handle is also kind of not proper location. This makes the editing a little bit more cumbersome, and you'll have to do remodeling basically. So whenever you have a situation like that, this is ideal to create a block. And a block is you create the geometry for one step, and reference that same geometry and repeat it and locate it wherever you want. So if you edit the original geometry, then that will update everything else. And all the geometry that you see in screen is just a matter of referencing that geometry to a new location and make the file much more lightweight. So I'll show you how to generate the blocks for the stairs, and we will basically recreate the stairs with the blocks instead of these steps. So now what I'll do is I'll just hide that pole, and I'll leave the scaffolding and make it my current. And perhaps I want to still use the, step, you know, these curves that I use to generate my step, which is these lines. So let me just go to ghosted mode here. And I want that curve. I want, what did I need? Oh, these curves, these reference curves that I use to generate my step. And I'll just move them to the scaffolding layer so I can see them here, and I can turn off this. So this is my step. Now, when you need to create a block, and let's actually take one of those guys, this extrusion and the point here. And as a matter of fact, I can immediately select this geometry and turn it into a block. So why not do that? Let's call block command. And my base point for my block will be for my this first block is basically the center of the of this. So I'll use the center snap, and I'll just use that, and I'll call it a step, and okay. Now this one is now a block. If you go to properties under details, you can see this is a block instant. Okay. So I will move this to a new layer, which I'll call step block. And I will just move this part to the step block. Okay. So this one is inside the step. Oh, that's misspelled. Step block. And I can hide all the rest of them and keep the step block. And the block has disappeared. Why? Because this one is, where is it? It is in the step block, but it's not visible here. Let's do this, turn this off. Okay, now, for some reason, this one is not moving. Once it was created in there, although I'm selecting, the other ones are in the step curves, and this one is in the step block. Quite strange, to be honest. I don't know why it's still there, but so what we can do is invert to select everything else and hide it. Let me lock the, okay, select it again, the block. I will lock the scaffolding, invert, and hide everything else that we created so that we only see the block here. All right. Did we select the point to be part of the block? Yes, we did. So now once you have a block instance, as we have here, you can now repeat the command, and all it does is just copy the block information to create the array. So array polar, and the center to be here, same, everything, and you know, created all the different ones. Now, if you select on any one of them, you will see under the type as a step block. And if you go details, you'll see this is the block instant, right? Now I have all the steps. If I want to edit the block itself, so you can do block edit command, and you select your block. You can see that it just kept the instance that you selected and grayed out everything else. Now you can make changes. For example, I can select the bottom of that surface and move to make a bit thinner steps, right? I can add an object, for example, and you select an object to add to the block. I haven't created anything, so I'll just go escape that. I'll just create a sphere, for example. And the sphere will be here at the center, and maybe 0.03. Maybe enter. So I'll say I want to add that to the block. So I'll just add an object and select the object to add to the block. Well, it actually became part of the block here. That's interesting. Oh, because I drew it inside this step block. Okay. So let's say OK. And what happened is once I edited the block and created all that, so any geometry I created while I was inside the block edit command, it kind of added this object and made the changes, which changed the thickness of my step and also added that sphere to it. So that make editing much easier than if you were to create it individually and then edit it. I probably can add another object, so I'll create a loft between this circle, and I have between this circle and this one. This is not a full circle. So let me just copy that circle from the center here to the center of this guy. And I'll just create a loft between the inner circle and the outer circle. And enter and cap it. And now I can add that object to my step, so it will be repeated all the way there. So what I'll do here is I'll do block edit again. And I'll select my block. And we'll add an object here, and I will add that surface that I just created. Press OK. And enter, and that became part of my block. Press OK, and as you can see, it was repeated all the way up there. It's still rendered, and that creates, you know, all the changes that you have generated here. So yeah, I think with that you can really get the idea of you know, how blocks work, and you know, the details of how to create those and what commands to use are detailed in this page. So any questions related to blocks and how they are created? Yeah, you can see the benefit of generating blocks and how it's easier than using history, for example. Of course, you know, there are certain cases where you need to use history, like when we did the lofted surface. But if you have a repeated geometry and you want to make it sort of parametric to be able to update at a later stage, you know, this step is a placeholder, but I'm going to change its design. You can generate it as a block, change the design, and then that will update all through without having to remodel again.
Raja, if I could
Yeah.
get you to go over the loft command when you added that like cap below the step.
Oh, yeah, sure. So I wanted to generate this little cap, and in order to generate it, I needed two curves. So I wanted that inner and outer curves. So initially, I didn't have a reference curve here to be able to loft between the two. So what I did, I copied that curve all the way up. And once I have two reference curves to use, this one and that one, then I can use them to create a lofted surface in between. So you do a loft, and let me just delete that block instant. It deleted the whole thing. It deleted the block instant. It actually deleted the block instant, not the surface itself. So let me see. This is the poly surface. So I'll take it aside along with the curves. I'll make a copy, and it's going to be easier to see here on the side. So what happened is I had these two initially, so I create a copy all the way up here and used Loft Command to loft between this and that, and press Enter. And that created the lofted surface, but you see it's just a thin surface, hollow. You can use Cap Command to cap it, and that make it more solid. One of the other things I should have done is I have to the pole, which is the cylinder. If you recall, let me just remove the intersection and the near. The pole that I had was, you know, I'm going to use grid snap. So let's say it was like that. And so I needed to do Boolean difference so that it's more proper. If you delete that, this is need to be hollow here. So that makes it a bit more proper as a piece if you want to really be appropriate in terms of your modeling. Yeah. So, but that's how I created that part and then added it to the block. It became all together as one block. And the block can have multiple objects in it. And you can remove some parts, you can add some parts. Let's remove a part, for example. So we go block edit and we select the block. And I can say I want to remove part of the block, which is my sphere, for example. And go OK, and that removes the sphere from everywhere else, right? This is the actual surface that's not part of the block. So the block is still just that part. So you can always add objects, remove objects, or edit objects within the block itself. And that updates all the way. Okay, does that help?
Yeah, that's good. Thanks. Cheers.
Yep, of course. This is considered kind of more advanced modeling topics, and now we kind of covered everything there is to do within Rhino to make it parametric modeling. We did the history, we did the blocks, but as you can see, you know, there are limitations here. And if you want a fully parametric model where you actually can change, you know, the width of the house, then you want everything to change with it. it's obviously not going to happen, and you will have to do remodeling or extend certain kind of surfaces and trim them and all that, which can be cumbersome, but doable. But if you are after creating a fully parametric model, then you need to use something like Grasshopper. So I'll just open a totally new file, and I'll just use my house as a template and open. And I thought it's a good place here to introduce a Grasshopper, since we talked about the parametric aspects of Rhino, to see that we have an environment within Rhino that is fully parametric. So I'll just create a skeleton of my lighthouse using history and show you some of the limitations that I have. So if I do a rectangle from the center here, and I will snap to the origin, and it's 4 by 4, and that's my base, right? And I can have this copied up, and I want it vertical from the center, and the height could be, I don't know, it depends on number of floors we have. So let's say it's 12 meter, and press enter, right? If you recall, when we created the lighthouse, then, you know, we extruded, we created the, let me create a line here also from here, and let's create the line to be vertical from the center as a reference, and you know, let's say it's 13 meters, and that's the end of it. And I'll create a point at the end, just creating some reference geometry here to generate my my lighthouse. So if I use history, for example, I can do some parametric design of the lighthouse. So for example, I can do a record history and do a loft between the base and the top, and I'll just, yeah, it's normal, and I don't simplify because I want it just to be all the way, you know, following my shape, and okay. And I can create, let me do ghosted. And I can create extrude curve to extrude curve to a point. Just remember to hit record history down the bottom here, and select my curve again, and press enter, and all the way to that top point. All right. So I have sort of the shape there, and I have some parametric control in that if I select my original curve and scale it down a little, you know, my form get changed as well. But then what about the floors and the thickness and the rest of the details? Sometimes, and what if I want to change the height of the floors or the number of the floors? That becomes much less flexible if you do it directly modeling with a Rhino. But if you have a Grasshopper, and by the way, did you all have a chance to look at the first couple videos that I sent the link to in the email, just so that you know the general interface of Grasshopper? Are you all comfortable with the working environment, or you want an overview of it?
An overview would be nice.
Okay. So let me close that, and I'll also make this, maximize that. So this is the Rhino environment that that we have. If you've never used a Grasshopper before, the way to access the parametric window or environment within Rhino is to either press Launch Grasshopper or type Grasshopper. and that opens this window which where you can put or build your parametric model. Actually, let me make that a little smaller and open them side by side, kind of easier to look here. I'll just delete those. Oops. Just delete some of the surfaces I created. I'll keep the reference curves here. And so that opens this is the Grasshopper window, which has the menu at the top, but more importantly, it has all these tabs, which has certain kind of icons or buttons in each one of those. It opens with the parameter, and this is the canvas. So with right mouse click, you can move the canvas around, and this is where you can have your functions or your components composed. If you double click with the left mouse on the canvas, you can have a keyword search. So for example, if I want a circle, then I start with typing CI, and it shows me all the different ways to create a circle or any kind of component that has a circle in it. So for example, this is a component to create a circle by a plane and a radius. So that's my circle, right? And the other way is to go to curves, for example, under primitive, and then you click on the circle and bring it to canvas. These are identical. I think, why don't we open a document, which is one of the ones that I sent to you guys. So was it I think it was detailed modeling. Let me see, under this one, the algorithmic modeling, O2 algorithmic modeling. I think I sent that file to you, and you open it. And that opens this file that has some circles or some components already constructed here. So the way you generate anything with a Grasshopper is by using what we call components, which is a certain function that takes some input and give you some output. So I'll right-click on it and click preview, and you can see that circle now generated in a preview. If I'm selecting it, it's green. If I'm not, it's red. You can change the radius of it. Double click on the panel and change it to 2, and that will generate a radius of 2. Really, when you have a parametric design, you'd want to kind of experiment with the circle radius ranging between 2 values, and we use what we call slider. And the number slider, you can double click on it and set it to be between 2 values, for example, between radius 1, for example, and a maximum radius of 5. And instead of hooking a panel or some parameter into your component, you can hook by left mouse click at the end of any component and feed it into your component here. And now if I click with the left mouse, you can see my circle changing the radius between 1 and 5, right? And that's what we call a parameter. Now the radius became a parameter because I can change it at will using whatever input method. The input could be direct, through panel, through slider, but it could be from another component that calculated that distance, right? The center as well, you can, select it or, specify it to be at certain location. So the think about Grasshopper is, and once you have it parametric, it becomes really easy to have multiple inputs. For example, here, if I preview, let me just hide those. You can see that this circle now, just because I fed it multiple radii, it just generated 3 circles for me, which I can go double click and change that to be any number of parameters, and I can quickly change those. So this is more of a programming kind of interface, or a visual programming, if you will, to be able to generate a fully parametric environment there. If you understand the concept of generating definition using a set of input, an operation, and then you get an output, that's basically all there is to it. And you can get the details of, how to use Grasshopper, and just go through the link of the introduction and the advanced Grasshopper, and that will give you a really good idea in the span of an hour or two about how Grasshopper works. If you want more details to be able to go through the details, go and use the essential algorithms and data structures, and that's some more in-depth understanding of how Grasshopper works. So now I'd like you to actually open a different one, which is the O2 GAM definition cluster Grasshopper. And this one is, where is the actual thing? Yeah. This one is an example of a definition which has some parameters as inputs. It has some solution in the middle, and I just put the solution all together in one cluster, so I spare you from having to see the details of it. But then you can capture the output into other components as well, which are parameters, what we call parameters. So this definition creates a lighthouse by taking an input curve, which is the base curve, and we can reference it in Rhino. And it has a number of parameters. So let's right-click on curve, CRV, and set one curve. And let's select the rectangle that we have here. And that generated a basic lighthouse using the solution that I put together here in the middle. And the output has a body part. See, when I select it, it turned into green. Let me just hide that first so we can see it more clearly. So this is the body part, this is the roof, and this is the floors, and this is the railing. Just basically 4 components here in the lighthouse. And remember, I can reference one curve or multiple curves. So for example, if I had a circle here in Rhino, I can select that to be my base curve. So I can right click on curve and say, set one curve to be my circle. And now that becomes my base curve to generate my lighthouse. I can even select multiple curves. So I can select the square and the circle. And that didn't work. So the whole solution wasn't designed to be able to handle multiple curves. So let's just say this is only for one curve at a time. So the nice thing here is that I've been able to use any kind of base curve as a reference and change the shape of my lighthouse. But I also have some parameters. For example, the top floor scale factor. So if you want it tapered a little bit, then you can have a scale factor for the top floor. You can also control the height of your floors to be between 2.8 and 3.2, for example. You can say the number of the floors, set them to be somewhere between 3 and 8 floors for your lighthouse. This is because you simply wanting to create a solution for a lighthouse, but you want it to be generic enough because sometimes your lighthouse has it's rectangular, sometimes it's circular, sometimes it's 5 floors, sometimes it's 8 floors, sometimes you want it tapered, sometimes not tapered. So this solution affords you to use the same kind of definition or you know, basically same solution to generate all different kind of lighthouse. Sometimes you need to interface with the client, or you're not sure about the final specifications, so you use parametric modeling to design your solution or model in the ballpark of where you want it to be, but have the flexibility to be able to go in and be able to change it if you need to. And the whole thing changes without having to go back to modeling it from scratch. So the floor height, the number of floors here, the scale of my observation deck, and the height of my rail to be in between certain kind of values. So all these things on the left are considered to be parameters because I can change them. And this is basically the output of what I get on the other end, and this is the solution. If you want to see what it took to create this, I'll double click on it and you see this is what's inside the cluster. Which is all the different kind of steps that I use to generate my lighthouse. All right. Now I go back to my definition here. And yeah, so, you know, obviously I'm not teaching you Grasshopper within half an hour here, but I just wanted to show you what does it mean to have a parametric kind of fully parametric solution and how to achieve it within Rhino using the Grasshopper environment. If you have any specific areas within Grasshopper that you'd like me to explore, if you haven't seen it before, if you want more kind of basic examples, I can probably go over that. But I just thought, you know, this is a general introduction. The best way to go about it is to go back to some of the videos that I sent for you, which is just the introduction, and it will show you how to, you know, just you can go introduction to Grasshopper. And then there are a lot of videos to just really go over that, and lots of guides as well. The one I sent you is this Rhino tutorial, I think, and it has multiple videos to show you the different, you know, interface and the workflow within Grasshopper. Yeah. Do you have any questions? No? Yeah.
Just one quick question.
Yep.
As we kind of say learn Grasshopper in the future, would you recommend at the end kind of like a blend of Rhino and Grasshopper? Or if we're really good at Grasshopper, maybe Grasshopper can do everything that Rhino can do?
Yeah, I think it's an usually a combination is the best. For example, you saw the staircase that we had. If you have any kind of, you know, you can take a component or part of your model and do it in a Grasshopper. Or maybe if you have a sophisticated wall kind of art that has, you know, some kind of uses certain kind of curves that need to be controlled in certain way. You know, you can have a feature within your model that uses a Grasshopper that is hard to model and modify within Rhino. And this is typically, you know, the best way to go about it, unless if you you know, there are cases when you have, for example, the lighthouse here is you want to create variations of the solution, and you want to quickly use, for example, a polygon here, and you know, I just want to explore the different kind of base curves. And, you know, I create a study model this way using Grasshopper. But if you want to create the whole house using Grasshopper, and it's a one-off model that you are creating and that's it, then it might be a little bit an overkill, I guess. It's really up to you. The other thing is that you might have a concept that you want to be able to change later without remodeling. So you say, no, I'm going to create the whole thing in Grasshopper. So I don't think there is like one answer for everything, but the good thing also about Grasshopper is that there are lots of plugins. So if you go to Food for Rhino, you will see that there are numerous number of plugins for Grasshopper that does all sorts of additional functionality that you don't have within Rhino. For example, you want to do environmental analysis for your model, then sunlight analysis or structural analysis, or you want to create schedules. So there are all sorts of plugins there that can take your model and you can do that extra work with it. So that becomes extremely handy. But yeah, I don't think there is like a one answer to it. If you are really proficient in Grasshopper, I think it's really good if you can create the parametric model, because then you can use it as basis for future modeling. But also you'll be able to do all the changes very quickly. You know, you're going to put some time up front, but you're going to do any change later very, very easily.
Thank you.
Yeah. So has any of you used the Grasshopper before? Yeah. Yeah. What are your impressions? What are the difficulties, or what are the advantages that you find using it?
I've only used it a little bit, and I tried to create like a spiral staircase using Grasshopper, and yeah, I didn't know polar array, and yes, mostly not really understanding how everything works in Grasshopper, just following like a tutorial online to create that specific thing, and then exploring from there. Yeah, it's I think probably the best practice is to create a lot of different models using Grasshopper and expanding that knowledge.
Essential algorithms, and data structures. I think I have linked to it. This one. So it is in Food for Rhino, so you can see it there. So this is a manual. So you can just basically download by going here, put your email, and download. And this one is an extensive manual that really make you very proficient in Grasshopper, and has everything that is all the definitions inside the manual are in the in there. So this one has you know, it starts with how to design an algorithm, which is, you know, Grasshopper is an algorithmic design environment where you will actually need to know how to do sort of a programming. So you need to know how to build a solution, how to build an algorithm, and this is the hard part. So that walk you step by step through how to design your algorithm, what are the algorithm parts, how to build an algorithm from scratch. And then after that, it really tells you about the data structure in a Grasshopper and the introduction and advanced data structure. So this is really everything you need to be very proficient in it. And it starts with describing what is an algorithm, the parts we talked about, which is the input, the algorithm steps, and the output you want to get. And, start with a very simple examples, for example, the addition and what have you. And every single example here is also attached to the manual itself. So this takes you all the way to generating, and there are tutorials at the end of each chapter. So for example, you want to do a variable thickness pipe tutorial. It shows you what are the steps, how to analyze your solution, and how to step by step be able to generate it. So it's really, very, very excessive and detailed. And, you go all the way to that last example where you actually generate weaving kind of pattern here, and just tells you step by step how to think about it and, how to generate it. So, from very beginner to very advanced material, but you'll need the basic understanding of the interface and how to string things together before you get in here. But this is, I highly recommend that. This is very highly used and it's very helpful. Yeah.
Oh, that's perfect. Yeah, I'll take a look. Thank you.
Yep. So I guess now that we have done that, are there any modeling related questions that you'd like to cover that we can do? We have some time remaining here. And let's see.
Oh, I had one more question on the curvature analysis. It provides like a, I think, a minimum and a maximum value. I was just wondering what those represent. And
so so this is the minimum and maximum curvature value. So the curvature is the rate of change in direction along the surface, if you will. You can think about it like that. So if you have a circle, then or a line, your curvature is not changing, it's constant, because along a line you're going the same direction all the time. With the circle over 1 unit length, the change in direction is also constant, although you're turning. Does that make sense? So this is considered 0. But if you have a free-form surface or a free-form curve, then the rate of change is going to change over 1 unit length. And this, when you have a minimum and a maximum, then this is the minimum and maximum change in curvature within your whole surface if you take a sampling all across. So that's what the number represents. Does that make sense? So let's open, for example, the roof here. And let me turn on that patch. And that's our surface. And if you go and do analyze surface, and I think with curve is easier. Let me just create a curve here so I can explain a little better. So I'll create a line. I'll create a circle. And I'll create a curve. Okay, so we have these 3 curves here, and we will do a curvature analysis here. So we'll do analyze curve and curvature graph. Okay, so this and this and that. And it's just because the feedback, the curve here, that changed the color to red. And the density you can increase or decrease, and the scale a little bit so we can see. Okay. So as you can see that this is just represent the amount. This line or the length of it is the curvature value, if you will. There is 0 for the line. There is no curvature, right? For the circle, there is some curvature, but it's constant, as you can see. As we go around the circle, we have really constant length of these segments, right? And this, along that curve, you see that the change of curvature is going from positive to negative to positive, and then the rate sometimes is steep, the curvature here, and sometimes it's kind of more shallow. And this is how you can read the values here of your curvature, you know, for the circle, for the curves. So, and that's I didn't show that in the examples how to analyze the curvature. I think I had one example with the central curve of the roof, but this is the value of, you know, this is the curvature there is. Now analyze curve. Now if we have a surface, let's do perspective here. And likewise, create a plane. Or just extrude those curves. Okay, so now we have these 3 surfaces and we will do a surface analysis for them. Actually, for that particular one, I'm going to, this is just an extrusion, so I'll just do a loft because I want to change, make it a bit more interesting. This and that. Okay. So now I have these 3 surfaces and I want to analyze these surfaces for a curvature analysis. If you choose the plane, you can see that everything here is green, solid green, which is 0. That means, you know, there is no change in curvature on that surface. And 0 is green, and you can just do an auto range. It's going between 0.1 and minus 0.1, but none of these colors are catching here, right? Let's add an object here. Let's add this. And as you can see, it's also solid green because the rate of change is not changing. No, there is no change in curvature here. And this is what the value is. And this is why it's a green. If I add this one, okay, I'll auto range them again, just because the values are really, the change in curvature is really minute. So this way we can have these values, and you can see because we have our units in meters, the number here is very, very small. But you can see that this is starting to have some colors on it because there is some kind of change in curvature in that particular surface, right? Well, it's not for the other 2. The mean curvature, I think, will give you a little bit more information here. It's that's also 0 here and a little bit more. You know, the difference between minimum and maximum curvature here, and this is the so there are 2 main curvatures: the Gaussian and the mean curvature. I can explain what those are, but I don't want to overcomplicate it. But for those numbers, this is the range of curvature between the minimum and the maximum there.
Oh, no, that's good. Thank you. And yeah, I was just thinking about kind of the functionality of it when we're designing, but I guess it's probably more helpful for the engineering side of it, would you say? Or
yes, exactly. You do have a little bit of use for it is if you want to see if your surface, for example, symmetrical or not. So for example, when we had a patch there for the roof, and let me just get this here a little bigger. And if I click on it, I click on my roof and do a surface analysis, and that's curvature analysis. This is like false color. Add objects. Adjust the mesh. I'll just make it more smooth. So it's easier to see. As you can see here, that really not symmetrical. Maybe it wasn't very clear when we didn't do the surface analysis, but you can see that the change in curvature here in that surface is definitely not symmetrical. I can see all these little patches of colors here. I'll also auto range, and sometimes actually the mean curvature give me a bit more idea. And that you can see that sometimes there is an abrupt change between one color and the other, and that really speaks to the smoothness of your surface as well. So as a designer, you can catch certain things. So from the surface analysis, using, just trying to see if it's symmetrical, you see how smooth it is. But you are right in that, there is more engineering information there. For example, if your analysis is all solid green, which is like 0, you know that you can unroll that surface. So in terms of a cylinder, you can unroll it, while this surface, you cannot unroll it without stretching it at certain spots. So that tells you like how expensive it is to build that surface.
What do you mean by unrolling it?
So for example, I have a cylinder here. If I do unroll surface and select my cylinder, it can unroll into a plane, right? Because imagine the cylinder, it can open up into a plane, and then you can use a roller. In real life, when you create panels, for example, there is a roller where you can roll it into a surface. So that's unrolling the surface, and this is how you create your panels, for example. So for example, if you have, you cannot, if this is a sheet metal, it starts as a sheet and they roll it into that shape. But with this kind of thing, you cannot really unroll it. So if you go unroll surface and I select this one, it really tells me that it cannot really unroll it unless it does some stretching, basically. So it's not easy to. And we call those surfaces that can be unrolled developable surfaces. Okay, that's just a terminology. It did unroll it, but it did report that it had to stretch it a little bit at certain areas. So you cannot go from this planar one to this one easily. Yeah. So that's basically, why it's really important to know once you create a surface, am I going to be able to build that surface easily? Is it going to be costly? Do I need molds or can I use rollers? So for example, if you have flat panels, these are the cheapest. If you have panels that are rolled, this is the next. Say, for example, this is double the cost of that. But then it becomes 10 times the cost if you have to create molds, for a unique shape panels. And this is where like your decision as a designer when you create a form is really important.
I see. Thank you.
Yeah. But this is really advanced question. So, thank you for asking that. And it tells, what you're looking for here. So within Rhino environment in general, like the two major functionalities that we will cover next class is the visualization, which is the rendering part, and the 2D layouts. And basically that's what we'll go over. And in the actual document here that we have, I guess what I'd like you to do is, if you can, want to practice a little bit, you can create a blocks of certain kind of forms, and you can finish off all the outdoor and the interior kind of modeling. Yeah, this is a little exercise where you actually can, just trace a sketch that you have and be able to bring it into your model. So that's what this exercise is for. This one uses Paneling Tools plugin. So if you have that one, then you can follow with this exercise. But due to kind of limitations with you guys not being in the lab, you might not have that plugin downloaded. But this is a free plugin for Rhino, and it's developed by McNeil. So this is really useful for paneling. Yeah, so you can follow up with, for example, you can use that plugin as well to generate the panels and redesign your roof to be fully developable and easy and more cost effective. So that's what this exercise is about. We will pick up from advanced visualization next week, and we will also cover the or try to cover the 2D drawing part, sectioning and the layout basically, and how you can organize all your drawing to scale in a paper space and be able to do the printing part. So that's what it is. I don't think we will have time to do more of the prototyping, and that will also need the lab to be able to do the laser cutting and prepping your model for 3D printing